Great, thanks. Yeah, thank you for the invitation, and thank you for letting me give this pre-talk. I would like the pre-talk to be like very casual, so please feel free to interrupt me at any time uh, for any reason. I'm happy to go over any portion of this in more detail. There isn't really a set end goal for the pre-talk. Um, Today I'll be talking a little bit about mirror symmetry and Lagrangian torus fibrations. And I want to kind of give some very, very concrete examples of like where at least my intuition for this relationship comes from. What is mirror symmetry? I feel like it's grown out to be a huge web of different pieces of interconnected mathematics, but at its core, it's a conjecture between two types of geometry, which are symplectic geometry and algebraic geometry, um, broadly speaking. And for historical reasons coming from physics, these are called the A-side geometry and the B-side geometry. I'll call them the A-side and B-side geometry simply because writing out symplectic geometry and algebraic geometry takes a lot of time. Also, the word symplectic doesn't make a good superscript on your spaces. So if I write XA, I mean a symplectic space. And I write XB, I mean an algebraic space. There's supposed to be this relation between symplectic geometry and algebraic geometry on two spaces. They're called mirror spaces, and I'll write them as XA and XB. And furthermore, they're supposed to be related via a third space Q, which is a space which they both have a fibration over. So let me just say something about what this A side and this B side geometry is, so everybody's on the same page. So on the A side, we have symplectic geometry. So what's this? A symplectic manifold is a 2n dimensional, so this is real dimensional. And I will call it XA with a 2 form, omega. This is real value 2 form, such that, well, I want it to be closed, so d omega is equal to 0, and non-degenerate. So when I take the nth power of omega, I get something which is not 0. So I get an area form. Oh, sorry, I get a volume on the space. These manifolds are very flexible in some sense, in that they have no kind of local invariance. So unlike if you were to look at, say, Riemannian geometry, where if you look at a small piece of a Riemannian manifold, you have an invariant, like the curvature that distinguishes one point from a different point. The symplectic manifolds have no kind of local invariance. Every point of a symplectic manifold looks like every other point of a symplectic manifold. Like the local model for a symplectic manifold would be something like R2n with the symplectic form sum from I equals 1 to n of dxi wedge dyi. So the coordinates on R2n are x1 dot 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 xn comma y1 dot 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 yn. This is some kind of interesting geometry that you can look at if you're coming from algebraic geometry. Every Kähler manifold is an example of one of these things, where the Kähler form is closed and non-degenerate. So that's one area where these show up a lot. Classically, they come from the geometry of physics. So let me introduce an example of a symplectic manifold, which will be kind of the only example of a symplectic manifold that I would use this talk. So the examples comes from cotangent bundles. So let M be a manifold with coordinates Q1 through Qn. Then the cotangent bundle of M has local coordinates Q1 through Qn, comma, P1 through Pn. So these are the coordinates in the dqi directions. So then if I take omega to be equal to the sum of dqi wedge dpi equals 1 to n, I get a symplectic form. So I get a closed non-degenerate 2 form. And here at the very beginning, I said that I had some local coordinates on M, but if you trace through this definition and you do the proper checks, you can see that this form omega over here doesn't actually depend on the choice of local coordinates. So the cotangent bundle is an example of a symplectic manifold, and it comes with an even canonical symplectic form. Relating to the previous example of R2n, here we're thinking of R2n as the cotangent bundle of Rn. And because everything is kind of locally modeled on R2n, these cotangent bundles serve as very good kind of slightly bigger than local models of your symplectic manifold. So it's very common if you find a symplectic manifold to find a cotangent bundle sitting inside of it. What do I mean by that? In symplectic manifolds, there's a special kind of a submanifold which we study, which is called a Lagrangian submanifold. So definition, a submanifold L inside of XA is Lagrangian if the dimension of L is equal to n. So this is 1/2 the dimension of X. And omega restricted to L is equal to 0. So these are submanifolds on which the symplectic form vanishes. Note that n is the largest dimension on which this can occur. So if I let my dimension get any bigger than n, then I will necessarily have a manifold on which the symplectic form is non-vanishing because it's non-degenerate. So this is kind of the biggest thing on which you can have a vanishing symplectic form. Maybe what's a good first example? So if I took Rn inside of R2n, then this is an example of something which is a Lagrangian submanifold. So maybe from the perspective of complex geometry, these Lagrangian submanifolds are like the real, like the totally real submanifolds of your space. Once you fix this, symplectic form. And there's kind of a fact, which is that every Lagrangian submanifold in XA has a neighborhood that looks like a portion of the cotangent bundle of T star L. So just like we said that every space was locally modeled on R2n, if I find a Lagrangian submanifold, I can find a local model that looks like the cotangent bundle of that Lagrangian submanifold. And that maybe this ties into the previous example. So when I have M inside of T star M, it's a quick check to see that the submanifold M given as the 0 section is a Lagrangian submanifold of T star M. Okay, so these are the things that I'm going to be playing around with on the A side, on the symplectic side. Maybe before I go on, are there any questions about these objects.
There are no questions in the chat for now.
Okay, great, thanks. Okay, so this is one side of the story, and now let me talk about the other side. So the B side. So this will be maybe algebraic or complex geometry. Okay, so you'll have to forgive the way that I phrase this is going to be phrased from a very, very differential geometric standpoint. So definition, an almost complex manifold is a 2n dimensional manifold XB with a bundle isomorphism J from the tangent bundle of XA to the tangent bundle of XA such that J squared is equal to minus the identity. Okay, so the obvious examples to give is if XA is complex, then multiplication by I gives almost complex structure on XA. So every complex manifold gives an example of one of these almost complex manifolds. The reverse statement is not true. So there are examples of almost complex manifolds which are known not to be complex manifolds. So why am I going to phrase what a complex manifold is in terms of this structure? Well, it makes it kind of easy for me to describe some of the differential geometry. So the main example that I have in mind comes from tangent bundles. So given Q a manifold with connection on Tx, we obtain an almost complex structure J from Tx to Tx, which swaps the horizontal and vertical subbundles. Sorry, J from TTX to TTX. It should be, I apologize, it should be on. I'm sorry, I've made a lot of mistakes here. You get so given Q a manifold with connection, so that's a connection on the tangent bundle of Q, thought of as a bundle over Q. You obtain an almost complex structure on the tangent space of Q, now thought of as a 2n dimensional manifold, which swaps the horizontal and vertical subbundles of TQ. Okay, so maybe in local coordinates, if I think of TQ as having coordinates Q1 through Qn, V1 through Vn, then this is the almost complex structure that says takes J of partial Qi is equal to partial Vi, and J of partial Vi is equal to minus partial Qi. So it just swaps the tangent directions and the directions of the base with a flip. Okay, so now we can begin to see where this story is connected to the previous one, which is that both of these, I have a manifold Q and I have a way of kind of upgrading it to a manifold which is twice the size. And in one way, I'm going to get a complex structure, and in one way, I'm going to get a symplectic structure. Now, just as we had before, some interest in a very special submanifold in the symplectic side, there are preferential submanifolds in the complex side, which are almost complex submanifolds. An almost complex submanifold of xb is yb inside of xb with yb equipped with its own almost complex structure. And when I take the almost complex structure from JX and I restrict it to YB, I get the almost complex structure on Y. So if you are comfortable thinking about holomorphic or complex manifolds, this is exactly to be a complex submanifold. There's no difference. Maybe the example, though, which is relevant to us, is that if I take V inside of Q, a submanifold, then the tangent space of V inside the tangent space of Q is almost complex submanifold. So there's a nice way to almost complex submanifolds inside of these things. Okay, so now we have this this story about taking a space Q and upgrading it in two different ways to get a symplectic space and an almost complex space. So in the last 10 minutes or so, let me give an example of where this all works out extremely well, which comes from the story of affine geometry. So we're not going to just start with any Q, but we're going to start with a Q that comes with an additional special structure. So Q is called affine if there exists a lattice of full rank TZQ inside of TQ. So this also gives a dual lattice T star ZQ inside of the cotangent bundle. Another way of saying what affine space is the space which is glued together from charts that look like Rn. But when I glue together the charts, I'm only allowed to use SLN transition maps. So it's a very, very rigid space. In fact, there are not a lot of these things. The examples that are out there are things like R to n, or if I take R to the n mod Z to the n, and these are examples of these affine spaces. You can build kind of other ones, but in fact, during this talk and my next talk, I'm actually only going to be worried about R to the n. Right, okay. And they come with a natural type of subbundle or submanifold. So affine submanifold. Okay, so this will be something like V inside of Q, such that when I take TZQ and I restrict it to V, I get a lattice in TV. Okay, so these are lines slash planes slash other things of rational slope. So it's a very, very rigid form of geometry. Now, the great thing about affine geometry is that it has a very, very nice upgrade to both the symplectic side and to the algebraic side. So to upgrade an affine space to the A side, so we'll say given Q affine, let XA equal T star Q mod this cotangent bundle lattice. So it's easy to check that the translations by the flat sections given by this subbundle respect the symplectic form. So when I perform this action, I will get some kind of space that has compact fibers and is symplectic. So the main example is if I start with something like Q equals Rn, then what I'll get is, or maybe let's just start with R, then XA will be a cylinder. So this is the cotangent bundle of R mod the lattice. More generally, if I take Q equal to Rn, then XA is equal to, well, it's really equal to the cotangent bundle of Tn. But maybe another way of thinking about this is that it looks like a space like C star to the n. It looks like the algebraic torus, where the argument directions give you the directions of the cotangent fiber, and the real radial coordinate gives you the tangent, gives you the directions in Q. Okay. Similarly, there's a affine to B side upgrade. So given Q, which is affine, let XB be equal to the tangent bundle of Q mod the tangent lattice. Okay, now recall, in order to do this type of upgrade, I needed Q to carry a flat connection, or to carry a connection, but because I have a lattice, I can use the lattice to build myself a connection. Okay, so example, and this will be a little bit deceptive. If I let Q equal R1, then XB will be TQ mod TZQ, and this will look like, again, a cylinder. It comes with a complex structure. Identifying it with C star. So the complex structure that this thing receives is the honest complex structure that you have on the algebraic torus. Now, we didn't just have kind of a story where we had a symplectic space and almost complex space, but we also had a story where both the A side and B side came with these preferred submanifolds. And let's talk a little bit about how that enters into this. So given V inside of Q, which is affine, submanifold, then I can do two types of upgrades. I can take the conormal bundle to V mod the conormal lattice bundle to V inside of T star Q mod T star ZQ, and this gives me a Lagrangian submanifold. Or I could take the tangent bundle to V mod the tangent lattice subbundle of V inside of TQ mod TZQ, and this gives me an almost complex submanifold. Okay. And from this, you get this conjecture, which is there is a relation between the Lagrangian submanifolds of XA, the almost complex submanifolds, or maybe I'll write coherent sheaves on XB, and affine submanifolds of Q. Now it turns out actually being affine is really kind of too rigid of a qualifier to put on your submanifolds. There's just not a lot of these. So in the next talk, I'll talk a little bit about what the appropriate upgrade to this story is, which is where I place affine with tropical. And there is kind of a historically, or maybe not historically, like a 10 or 20-year-old understanding of how complex submanifolds are related to tropical submanifolds. And in the actual talk, I will describe this relation, the relationship between Lagrangian submanifolds and tropical submanifolds in some more detail, and then use those relations to study the relationship between Lagrangian submanifolds and complex submanifolds.